All right. Hi, everyone. Welcome back to Deep Learning Systems, Algorithms, and Implementation. Today, we're going to talk about our first of two lectures. This is sort of the more algorithmic lecture. Next will be the implementation lecture on sequence modeling and recurrent networks. So to give a quick outline for the lecture today, we're first going to talk about sequence modeling kind of in the general case. How does sequence modeling differ from the types of machine learning problems we've been dealing with so far? Then we're going to talk about one particular method for handling sequence models or sequence modeling in deep networks, namely recurrent neural networks, which is sort of a whole class of networks that we'll talk about today. We'll then talk about one particular instantiation of a recurrent neural network, which is an LSTM, or long short-term memory. And finally, we'll end by briefly talking about how we can use the techniques of recurrent networks and LSTMs to move beyond what I'm calling simple sequential models to more maybe complex prediction tasks that still involve some sort of temporal element. All right, so let's start off with and jump into the problem of sequence modeling in general. So sequence modeling differs a bit from the kind of problems we've been dealing with so far. So far we've been dealing with prediction problems for the most part, at least except for the generative modeling lectures we had recently. For the most part, we've been dealing with prediction problems where what we're given is pairs of x and y variables. Right? Those are the inputs and target outputs of our system. Right? So we're given a collection of these things. And the implicit assumption of most of our lectures thus far is that these input-output pairs, the collection that we're given, so our whole data set, namely, x1 to xm, etc., is what's called independent and identically distributed, or IID. And what that means in some sense is there's no inherent ordering to these points, right? It doesn't really matter if you do them if you see the first one first, the second one second. There's no inherent ordering, and all that really matters here is the collection of examples we're getting, right? That's been our implicit assumption so far, and we see that when we do things like reorder the batches. So if we reorder the batch or randomly sample our examples to create a mini batch, that's sort of implicitly using this assumption that our inputs are, in some sense, independent from each other. But in practice, of course, this is not always the case. There are many cases where the input-output pairs form some sort of dependent sequence, right? And in particular, we're going to consider the case here where they form some sort of sequential set of input-output pairs that will sort of use figures like this to denote. So we'll use figures like there's an x1 that leads to y1, but then it also influences somehow x2, which produces y2, etc. And this is not sort of to be clear, this is not kind of a strict causal diagram or anything like this. It's just sort of a diagram here that we use to remind ourselves that this problem that we're talking about today, where we have xy pairs still, but where the xy pairs are now ordered sequentially, we're just using this notation to remind us that these things are dependent in this way. Okay, so that's really what this notation here is for. Now, one other change we'll make here is that we're not going to use, for the rest of this lecture, for the most part, we've used kind of superscripts here, x superscript I and little parentheses here to differentiate, I guess, from exponentiation. But we've been using that notation to sort of denote the ith example in our data set, right? And we're going to move away from that today because, to be honest, it's just not very common in temporal modeling. What's much more common is to use subscripts to denote the index in time that an example appears in. But it's very important to note that in this notation here, in general, for all of these things, xt in this notation would be a vector. So xt would be some vector, say, in Rn. Previously, we've been using the subscripts to index into a vector. So x1 would be the first element of x. But we're not going to be doing that here. For simplicity, we're going to assume that kind of everything is a vector. So we're gonna make this simplification, which is somewhat of a hassle because now if we want to refer to the ith element of this vector, we have to do weird things like this and stuff like that. But For the most part, we don't do too much work that looks at the individual entries in vectors. We typically operate on them as vectors. So it's much more convenient to use subscripts for the sequence dimension, i.e. the time dimension. And we're going to use that for the rest of the lecture today. And so what we'll actually see is sort of figures like this that sort of show the temporal dependencies and the temporal sequence of things, but using subscripts here to denote where things are in the sequence. All right, now let me give a few examples of tasks that are sequence dependent, right? And one good example of this would be something like part of speech tagging in natural language. So the task here is that we want to take a sequence of words, like the quick brown fox jumped, etc., and translate, or rather predict from each of these the part of speech that each one of these is. So brown is an adjective, fox is a noun, etc. And the crucial point that I want to make here about this task is that this is a task that shows the importance of sequence modeling, and the fact that this is a sequence. Because if we had another element here, like it jumped well, the part of speech of well cannot be predicted just from that word alone, right? Well can be either a adverb describing how the fox jumped, or it can be a noun, right, describing like a well in the ground and things like this, right? So the important part about sequence modeling to keep in mind is that not only can the temporal dependence kind of help us make better predictions, in some cases, the temporal sequence is crucial for predicting at all. Because without the temporal sequence, there's just no way to predict what the next or what the true kind of label of this word is, right? So if we don't have a verb say beforehand, it would just be very hard to know what the temporal what the correct prediction would be for this part of speech here. Another nice example is speech to text. So the task here is we're given a bunch of audio or something like this, and we want to predict the speech or the words, the text of all these things, right? So we want to, I've given some sequence here. So this is actually a picture of me recording the phrase deep learning systems, algorithms, and implementation. And let's even assume that we're given sort of the correct boundaries. Let's even assume that we're sort of given all the audio boundaries here somehow. Doesn't really matter how we get that. Of course, in reality, this is not given to you, and you have to figure out what the word boundaries are. But if we're given these word boundaries, we now have another sequence problem, right? Another sequence prediction problem, because we're given a sequence of these inputs of audio here. We have to predict from them the word or the text that they correspond to. And again, to use a somewhat a bit looser analogy here, because I guess this example here would correspond to different word boundaries in this case. But another key element of speech to text is that it's extremely important to take in the word ordering and the temporal sequence here, and also just the dependencies between words in general. There's a famous sort of example of how hard it is to recognize speech, which, if you interpret it differently, could sound like recognize beach. And it just sort of highlights the fact that not only does the temporal sequence matter, it's sort of unusual to say the words recognize beach, but it really, the context and the sequence of words both matter in this prediction problem. And the last example I want to highlight here is a sequence prediction problem that's taken on special meaning in the past few years due to its extensive use in things like language models. And this is a setting of autoregressive prediction, especially autoregressive prediction for things like language. So to be very clear, autoregressive prediction is not the only sequence prediction problem there is. There's lots of sequence prediction problems like the kind I've already said. But autoregressive prediction is one special case of sequence prediction that has, again, taken on an outsized importance in recent years due to it being at the foundation of large language models. And the idea here is that we want to also make a sequential prediction task, but so we have some input sequence, which is, again, for example, a English sentence. But instead of predicting the part of speech or things like this, the task at each location is to predict the next term in the sequence. Okay, so at this point, after the quick, we want to predict the word brown. After sort of getting the quick brown, we want to predict fox, etc. Right? So given all the words up until now, we want to predict the next word. Or this can also, of course, operate on not words, but on characters or on tokens, kind of somewhere in the middle, but this is the basic idea here, right? And this is a very common problem, not just in language modeling, but also in things like time series forecasting more generally. And actually many use cases involve autoregressive prediction. However, right now it's sort of most well known for these applications in language modeling. And so what I want to emphasize here is, again, this is not all sequence prediction, of course, is autoregressive, but this is a one very particular example of a sequence prediction problem that we will come back to a few times later in this course. All right, so with that as some, and again, of course, the examples here is that the important point to note here is that this prediction problem, so predicting the quick brown and then predicting fox from it, this depends not just on the word brown. So if you just had the single word of the sequence, it would be very hard to predict what the next one would be. But given the whole prior sequence, even though you can't predict, of course, exactly, you can do a much better job at capturing the distribution over next tokens than you would be able to normally. All right, so let's talk now about one possible now deep network model. It's arguably deep network, depending on your perspective here, but we'll go ahead and call it a deep network. One deep network model for solving this problem, which is the model of recurrent neural networks. So the basic idea of a recurrent neural network is that we model a network that kind of, in some sense, mimics the temporal structure of our input sequence. All right, so we have our input sequence here, x1, x2, x3. But instead of trying to directly predict y1, y2, and y3 from this, we, in some sense, modulate our predictions through a hidden state which is maintained over time. And in particular, if we look at the update rule for a given hidden state, this is a function not just of the input of that time, but also of the previous hidden state. And then when we want to predict our output, we make this a function just of the hidden state. So we can write this more formally now. We can write this as our hidden state yt, so ht here, is equal to some function f, some nonlinear function. So this could be like the sigmoid, like the ReLU, like anything else. Some nonlinear function of a matrix WHH times our previous hidden state, HT minus 1, right? So this is a sort of, in some sense, like a multilayer perceptron. Of course, you can add more structure to this too. So these could be things like convolutions if you wanted, but more common to sort of start off with things is just thinking of the hidden state as a vector, thinking of I'm thinking of the mapping from our previous hidden state to our current hidden state as a matrix. Then plus some other matrix, WHX times XT, plus what I'm calling the bias of H. So plus a bias term of H. And particularly, let's also look at the sizes of these things here. So we're not going to dwell too much on the sizes of these things, but I should give some sort of simple examples of what these things could be. So here, HT could be a vector, say, in RD. So it would be a d-dimensional hidden state. let's say that xt would be an n-dimensional hidden vector. And just for the sake of it, let's say that yt, this really could be anything else, but let's just make yt real valued for now. Maybe actually, you know what, let's actually just make it an rk. So it could be something like, we've used the output values in rk before, so let's actually use y being an output value in rk. All right, and what that would imply, of course, is that w HH would be a D by D matrix. Oops. Move this over. W would be a D by D matrix. WHH would be D by D matrix. WHX would be, well, it has to map X n-dimensional inputs to D-dimensional hidden state. So that has to be a D by N matrix. And B here, BH, would of course then be a D-dimensional vector. So that's our state update for the hidden state. And similarly, we can write a function that sort of gives our predicted outputs yt. That would be some other nonlinear function of some matrix wyh applied to our hidden state at time t, plus some bias for our output. Where here, again, wyh would be, in this case, a k by d dimensional matrix, and by would be a k dimensional vector. Right? The sizes aren't too important here. What I really want to emphasize are the updates, but and in the future I actually won't give all the sizes always for all these things. I'll sort of assume that you know what the sizes would be in order for these things to make the multiplications work, but I want to sort of lay it out here explicitly. Now, to be clear, what's happening here is that we are taking our previous, when we're creating this current state here, again, what our update equations say is that this hidden state here is some function of our past hidden state and our input. And the really important point to keep in mind here is that our hidden state, because our hidden state, you can kind of see this from the computational graph itself, because our hidden state depends on the previous hidden state, which depends on the previous hidden state of that, which et cetera, in some sense, the hidden state at time t captures, or can capture, in the ideal case, all the inputs it has seen up until that point, right? Because the hidden state, h3, say, is a function, implicit, is a function kind of via this recursive procedure of x1, of x2, and of x3, right? There's a computational chain that leads from x1 to x3, from x2 to x3, and of course from x3 to, sorry, from x1 to h3, from x2 to h3, and from x3 to h3, right? So this hidden state here, and this is actually a really important point, it can capture, or in some sense summarize, all the information up until that point in the sequence. And in fact, if we do a good job of learning this recurrent neural network, then the hidden state really should capture all the information that we need to solve our prediction task at that point. All right, so that is, in a nutshell, the structure of a simple recurrent neural network. Now, the next obvious question is, how do we go about actually training a recurrent neural network? How do we, in fact, learn the parameters of our network, which would be, in this case, these matrices, right? How do we learn WH, WHH, WX, HX, the biases, etc.? And when you think about it, because these same functions here are used to form all our predictions, right? When you form H1, you use W, you use these terms. When you form Y1, etc. These are the parameters of our network. And we want to adjust these parameters so as to make our outputs here match some target outputs. So the way we're going to write that is that we have some set of input and output targets. And here I'm going to be a little bit, I'm going to change the notation slightly from what you saw previously, but I'm going to refer, because it's common to refer to the y's as the outputs of the RNN, I'm going to refer to the targets of our prediction problem as y star. So, y star 1 would be the thing that we want to predict at time 1, y star 2, etc., up to some time frame y star t. Okay. So this is the target sequence we have. And now, if you think about it, I think personally it would be pretty challenging to, by hand, derive all the gradients of some loss of, between my entire sequence that I predicted and this target sequence to derive the gradient of this loss with respect to all the relevant parameters of my network, namely all my weights and all my bias terms. Okay, but the good news about RNN training is that we don't need to worry about this. We don't need to worry about the precise form of the gradients because we can make use here of our automatic differentiation tools, right? And this is sort of the key aspect of that I would emphasize of RNNs, which sort of which really codifies how great automatic differentiation is, right? So I want to show you now kind of what an optimization loop would look like for an RNN, right? We'd form some optimizer like our SGD or atom E-formed in needle. We'd have our parameters here, which would be our weights, all the weights and all the biases, right? And now we would just sort of make our predictions. Right? So we would initialize our first hidden state to be 0. This is actually an important point that I didn't quite mention in the last slide. There's no equation for H0, right? There's no sort of notion of what this is. And in fact, when we talk about turning long sequences, we'll talk about this more in the next lecture. And truncated backpropagation through time is what we're going to talk about next lecture. But for now, the way to think about H0 is just initialize it to 0. So, I mean, of course, with a recurrent network like this, you have to pick what your first hidden state is, right? You can't form H. There's no sequence yet. You can't form anything. So just make it 0, right? That's sort of the simple thing to do. So set your initial state to be 0. Set your loss to be 0, and then iterate over your whole sequence. So from 1 to t. Okay. So from 1 to t, you form your next hidden state, right? Which is this update equation, a function of our previous hidden state and our current input. Form the output prediction, which is again a function of our current hidden state, and then compute a loss between our prediction yt and the true output y star t. And I'm writing this in sort of this pseudocode for a reason here, which is that I don't want to write this out algorithmically, right? Algorithmically, this is just sort of the equations you saw previously, plus some loss between y and y star. But what I definitely don't want to do is actually derive what the gradient is with respect to WHH of this loss, right? Because it depends on, WHH affects all these terms, right? There's influence on every HT on WHH and all the terms that came before it, and writing out these gradients would be quite cumbersome. In fact, people used to do that, right? It used to be when you sort of derived RNNs, you'd also have to derive these long chain rule gradients, and it's not that bad. You can certainly do it, and you can write them in recursive form and all this kind of stuff. But boy, it's so much easier to just write this, right? Because we've set this up, this whole chain of dependency in Needle or in our automatic differentiation toolkit, we can compute all the gradients by just a call to loss.backward. And this really, really showcases the power of these automatic differentiation tools. Okay, so we compute our loss, and then we just call op.step. Right, that's the optimization method. And this whole procedure here is often called backpropagation through time. Through time, or just BPTT. That is a B. BPTT. Backpropagation through time. Okay, so this is the algorithm that we typically refer to as backpropagation through time. It just basically means that we are explicitly unrolling our recurrent network over some time sequence, and then we are taking gradient steps over that whole time sequence. And as I said, next lecture we'll talk about a slight variant of this that actually we don't want to unroll our entire sequence, which could be intractable for very large sequences. You can approximate this by just truncating this procedure at various points. But we'll talk about that next lecture. All right, so that's actually all I'm going to say about training RNNs, right? And the beauty of it is that that's all I have to say, because we've developed this great automatic differentiation toolkit that really all we have to do is define, in some sense, kind of the forward pass of our network, define the loss function, and then we have right away our way of training this. All right, a few points of note before I talk about, I guess I would say, the problem or the challenges with RNNs. Because while this is, the previous slide in some sense conceptually shows how you build and train RNNs, if you just try to do that, these won't work very well, admittedly. So we'll talk about why that's the case. Before we do, though, I do want to mention one quick point, which is that just like all deep networks, RNNs are stackable, right? So you can stack an RNN to make a deeper RNN. And what this usually means here is that when we say deep RNNs, I mean, depth now has sort of two possible meanings, right? Because in some sense, we're already doing deep computations because we're sort of doing a chain of computations going forward in time. But when we say stacking RNNs, what we actually mean typically is that we take one RNN here and we stack another RNN on top of it. And what that means is that the outputs from the previous RNN, so the outputs from this RNN, become the inputs to the next layer's RNN. Right? So that's what we mean by stacking it. And note that this sequence like this still obeys the same temporal dependencies of our single layer RNN. In particular, Y2 in this computational graph is only a function of X1 and X2. I mean, of course, the hidden states too, but we don't worry about that. And similarly, that should be Y3 there. This should be Y3. But Y3 is only a function of X3, X2, and X1. Okay? Even when you stack these things deeper, there's no violation of the temporal dependencies here. Okay, now let's talk a little bit about the challenges of training RNNs. And the challenges of training RNNs are frequently called either exploding or vanishing activations and gradients. But I want to highlight both of these sort of two possibilities here. And to do this, I'm actually going to recall things we talked about when we talked about training very deep multi-layer perceptrons. So if you go back to the lectures we had on normalization and these sorts of, and normalization and regularization and initialization, right? One thing we saw was that when we trained a very deep multilayer perceptron, or even initialized a very deep multilayer perceptron, the initial weights of the network really mattered. Okay, so if you remember, so again, you can go back to that lectures. This, I think, it was lecture 5 or 6 or something like this. So again, maybe 6, maybe 7, around that time. So a long time ago now. But if you remember, we sort of looked at different initializations of these networks, and we saw that the activations of our inside our network would change depending on these things. And if you remember, like if we initialize our network normally with, well, really what we should do is initialize our network with weights as normal values, or what we could do is initialize our network with normal Gaussian values with variance 2 over n. That was sort of the sweet spot for a ReLU to maintain variance throughout the network. And if we had more than 2 over n, the activations would increase over the depth of the network. And if we had less than 2 over n, it would decrease over the network. That problem in the case of a deep multi-layer perceptron was admittedly a bit artificial, because we don't typically train, at least in that specific case, because we don't typically train, 50-layer deep multi-layer perceptrons. Okay, But the important point with RNNs here, so the thing I want to emphasize with RNNs is that a very similar pattern occurs. But unlike MLPs, say, RNNs, we actually are very naturally, in many cases, going to be that deep, right? Because we might have sequences that are 200 steps long or even longer, right? And those problems that we encountered in deep MLPs of activations blowing up or going to zero, those problems are all still going to occur here, and they're going to cause problems for us. So what I'm showing here is I'm showing actually a plot of a sequence in time, just an arbitrary sequence. I think I just use random inputs here. But what I'm plotting here is the norm of the hidden unit over this time period. And importantly, this scale here is exponential. So a little bit bigger here is much bigger. Like 10 to the 6th is the unit here. And in other words, just too big to really represent. And you know, what would really happen if you try to do this is you'll quickly get nans. This if you use 32-bit floating point representations here. So what I've done here is I've initialized my network. I'm using ReLUs in my network. We'll get back to ReLUs in a second, because we probably don't want to use ReLUs in recurrent networks, but we'll talk about that in a second. I'm using a weight matrix, WHH. That, again, that's my hidden to hidden weight matrix. That's the one that maps hidden, going back a few slides, that is the one that maps hidden vectors to the hidden state to the next hidden state. I've initialized that with sort of too big an initialization for ReLUs, right? So I've initialized it with variance 3 over n instead of 2 over n. If I do 2 over n initialization, it'll work, though it'll quickly diverge from that when you train these things. So I've initialized it here. And what we see is that just like in an MLP, the activations kind of increase over time, right? So they're blowing up, and the end result is you would get nans if you try to actually train this. And so this is a problem with RNNs. This is called an exploding activation, or again, what you would also get here is you would get, if you look at the gradients of this, you'll find that all your gradients, because your activations grow very large, all your gradients also grow very large, actually over the whole sequence. And so this is called the exploding gradient problem also. And of course, as well, the opposite problem exists too. So there's also the problem of vanishing gradients and activations. So if the weights are too small, so if WHH is initialized too small, say 1.5 over n, then your norm of your weights decreases over your sequence length, and your gradients will similarly decrease, and your gradients will be too small, and you will not be able to learn. Now, one thing I should mention is that this is actually only adding a non-zero input over at time 1, so that the inputs that I'm showing here for all times except time 1 are 0. That's important because if we keep adding new information, right, so if we keep adding another x term, this will in fact be able to stay non-zero, but this is actually kind of hiding the real problem. Because the problem here is that, in an RNN, we want to maintain what we're calling here sort of long-range dependencies, right? So we want it to be the case that at some later point in time, we can still maintain some dependency, or sometimes look back to point x1 in order to make our predictions at that later time, right? Otherwise, if we don't do that, we've sort of lost the whole point of RNNs in some sense. And if your weights are too small, you have this problem called vanishing gradients or vanishing activations, which means basically that the influence of previous time points, x1 over x10, say, gets smaller and smaller and effectively vanishes here. And it doesn't even take till, if you look at that, again, this is a log scale here. So very quickly, the dependency at point 1 will vanish, and there will be no real influence of your input at time 1 on the output here. Okay, so these are the two, I would say, core problems of RNNs: the exploding gradient problem and the vanishing gradient problem. And in some sense, dealing with these two problems has been the history of RNNs, or finding ways to deal with these two problems has been the history of RNNs. And there are a number of things you can do here. Of course, in previous lectures, we talked about normalization, and you also can do things like normalization. But one thing I want to emphasize, and in fact, there will be sort of very similar things that are done, but these don't really solve the problem. And in fact, the thing that I want to emphasize right now, which to be honest actually has similar effects as normalization, is just make one point about how we could possibly fix these things using nonlinear activations. So one sort of oddity of these previous two slides, right, these dependencies in the previous two slides, is that I used ReLU activations, right? So this is an RNN with a ReLU activation. And if you know RNNs very well, you actually probably know that they don't really tend to use ReLU activations for this exact reason, right? So I actually can get away from this problem if I just use my activation initially, or initialization, I can get away from this problem if I just use 2 over n as my activation. But as I take gradient steps, then I'm going to be changing this, and very quickly you'll get the same problem when you use ReLU. So very quickly you'll either have your activations blow up, or they'll shrink, and your gradients will therefore blow up or shrink. So ReLUs are sort of tricky to use, at least very finicky if you're going to use them. And so a very common thing to sort of think about is, well, why don't we just sort of normalize our layers, or i.e. why don't we cap the maximum value we can have for our layers by, say, using an activation that is actually bounded, right? This has a similar effect in some cases to normalization, right? And you can kind of think of them similarly, at least for the case of RNNs here. So for example, we could use the sigmoid activation, right? We could use an activation like this, which would limit the values of our hidden states to 0 or 1, or a tan-H activation, similar shape, which would limit the values to be between -1 and 1. Does this solve our problem? And the answer is no. This does not solve either the vanishing gradient or it does I guess it does solve sort of trivially, I would say, the exploding gradient problem and the exploding activation problem, because you've just limited your activations period, right? So they're just going to be smaller. There's no point in this with that large a gradient, and so with that larger term that has sort of a product of the gradient and the activation, and so you're not going to have sort of the exploding activation problem, as you can see here, because of course you're just forcing your activations to be limited to -1 or 1 or 0 or 1. So you're not going to have the exploding activation problem. But it turns out these by themselves don't solve the problem. And in particular, they don't solve the problem of the vanishing gradient problem, because one of two things will happen, right? You're either going to be sort of in this region here in your activation, in which case your activation sort of will stagnate, right? So think of the tan-H, right? Right in that central point there, the activations actually are 0. So if you're in the point with sort of a non-zero gradient, you're going to have your activations go to 0. On the other hand, if you get kind of in this region here where you have saturating, where you sort of hit the saturation point, in this point, the gradient of this function approaches 0, right? So here, the activation approaches 0, here the gradient approaches 0. And so if you start getting larger activations, you're actually in regions where your gradient is 0, and so your gradient is going to have a still vanish. And so essentially with these sorts of activations, and even though the sigmoid may look a little bit different because you're at 0.5 there instead of 0, it actually has the same exact problem. It's just sort of a constant shift. And so basically either you have you're in either a region with a very small value or a very small gradient, and this essentially will cause the exact same problems to happen here as you had before. And so the short story of this all is that there is just using these activations will not fix the problem of vanishing gradients. All right, and even if you use a saturating nonlinearity, you're still going to have essentially a vanishing influence between earlier points in your sequence and later points. So how might we go about fixing this? And there are many ways you can fix it, but one method that I want to highlight because it has reached such popularity in deep networks is to use a different architecture for our RNN. And one of the most famous of these is what's called the LSTM, or long short-term memory recurrent network. So an LSTM, which again stands for long short-term memory, what an LSTM is And again, LSTMs are often given this kind of outsized importance, and they are, to be clear, very historically important in sort of the evolution of recurrent networks. They were the first, or one of the first recurrent networks that really started to deal head-on with this problem of vanishing gradients, and or at least one of the very popular for initial ones. But in some sense, all they are is they are a particular form of hidden update they solve some of the problems of vanilla RNNs. So LSTMs are a particular form of RNN that solves to some degree, not fully, but they solve to a certain degree some of the problems of vanilla recurrent neural networks. And what I mean by that is just the recurrent neural network you saw on the previous slides here. So part of the confusion with LSTMs comes, I think, from the terminology that's being used. What an LSTM does is it takes this sort of diagram that we have on the left here, and it takes these hidden states, and it splits the hidden state into two different components that has two correspondingly different update rules. And these are called, very confusingly, the hidden state and the cell state. But to be very, very clear here, the cell state is just another component of the hidden state. It's not something special or different. It's just another aspect of the hidden state that has, in total, a different update rule. So that's the first step, is you're going to split the hidden state into these two different components called, again, very confusingly, the hidden state, but they're both the hidden state, to be clear. The hidden state and the cell state are both elements of the hidden state for this LSTM at time t. And then what we're going to do is we're going to use a very specific form of update for the hidden state and for the cell state. And I'm going to write these out here. I'm going to write exactly what they are. They're a bit cumbersome, and they're cumbersome because they use these intermediate states with weird names like the forget gate or the input gate or the output gate. And I think actually, so this is the input gate, this is the output gate, this is the forget gate. I think this is called not called the gate. It's going to G, but I think it's called the cell gate. We've already used the term C, so we have to use the term G there. These are very confusingly named, but let me just state what they are. All right, so what we're going to do with an LSTM is we're going to compute first these terms here, which they don't really have too much importance. They're just intermediate terms we're going to use to then form our updates of the next hidden state and the next cell state as a function of the previous one, okay? So these terms here, for some time, HT and CT, these terms will all be functions of sort of the previous states, and then we're going to form the next states as a function of these things, and I guess also the previous states. Let me just write what these are, and then we'll go from there. All right, so this uses the following update. Some nonlinear function of, first of all, actually, maybe also just define sizes. So all these things I should mention. So I, ft, all of these things, these are all going to be in RD, say. So assume that all these things are RD. So in other words, all these gates here are the same size. CT is the same size. HT is the same size. They're all d-dimensional vectors. Okay. So the update is going to be, we're going to form all of these things as some function of the previous hidden state plus, maybe I'll just write it like this. I won't use HH. I'll just use WH here. Actually, no, I'm going to use WHH, even though that's somewhat confusing because it's actually not mapping hidden to hidden. It's mapping hidden to all those things, but I'll talk about that in a second. Times WHX, just to use sort of consistent notation with the past one to make clear this is not that different from the previous RNN, plus a bias term here, BH. So that actually looks very similar to our previous update, right? The only difference, I guess, being that we're not using the whole hidden state here. We're only using sort of this portion of the hidden state to form this. And then we're going to apply different nonlinearities to this to form each of the different updates. So in particular, I'm going to write like this too, like what these different nonlinearities are. To get the I term here, we'll take this whole term here, and to get that component, we'll apply a sigmoid. The next one will also use a sigmoid. GT will be different. It will use, it's special, it will use a tan H. And the next one uses a sigmoid. Okay? The important thing to keep in mind here is sort of just understand what I'm doing here. So again, HT here would be a vector which is in RD. That means, by the way, the total hidden state size here would be 2D dimensional. Not 2D, but 2 times D dimensional. And so this vector, this matrix here, WHH, would be in R 4D times D, right? Because it's mapping an D-dimensional vector H to a 4D dimensional vector that we're going to split into 4 different components and call IT, FT, GT, and OT. And these are all, we get these by applying different sigmoids. But it's important to note that what this means is that we're taking W here, which is a large 4D by D matrix, forming all those different components and then applying different nonlinearities to all of them. And similarly, if this one here, if X was n dimensional, then this here would have to be 4D by n. Okay, so that's sort of the sizes of all these things. All right, that's kind of step one of this procedure. We're forming these initial things, and oftentimes if you've seen it before, you may see like this broken down into the different individual elements, like a input gate weight and a mapping from x's to the input gates and x's to the forget gates, but it isn't even implemented that like that internally in these libraries. There's always one matrix because it's better to use one matrix and then split things. So it's much better to think of these in analogy to a normal RNN as just having one matrix that just sort of in some sense inflates the hidden state a little bit, or inflates the state to 4 times its dimension for these intermediate terms here. And then now we're going to form the updates for these terms. And in particular, CT is going to be equal to CT minus 1, element-wise product with FT, okay, plus IT, element-wise product with GT. Okay. And then finally, HT equals the tan H of CT, element product with OT. All right, and now I want to sort of, look at that for a moment and just add like a suitably appropriate number of question marks, maybe exclamation points, something like this. Like what on earth is happening here? Like what did these updates mean? Why did we choose these updates? Like what do the equations actually correspond to? Now, there are a number of papers and blog posts and a number of descriptions here on understanding these updates and understanding sometimes how LSTMs work. And I find most of them rather unhelpful. I don't find much intuition, if I'm completely honest, in the names of these things. Input gates and forget gates and output gates. These seem to me rather arbitrary, and I think they are rather arbitrary. A lot of other structures work just fine here too. You can actually simplify a lot of these things and have other recurrent units that accomplish many of the same effects as LSTMs, but are simpler or just structured differently or somehow different. To be very clear, LSTMs have survived a very, very long time and survived very well because they've sometimes been tuned very well, and these particular equations do seem nice, but they are somewhat arbitrary. So I'm not going to go over kind of the intuition about what each of these things is doing and why it makes total sense to not call them the input gate and the output gate and the forget gate and the cell gate, all kinds of, because I actually don't think it makes sense. What I'm going to try to do is describe the key aspect by which I view LSTMs, and try to explain at a high level why these things at least help to avoid the vanishing gradient problem we saw in previous vanilla RNNs. And the key line that I want to highlight is this line. So what is this line doing? This line is forming the current cell state, which again, the cell state is just an element, a portion of the hidden state. It's the portion that's maintained over time. Part of the hidden state, basically. And the way it forms the hidden state at time t, or the cell state at time t, I'll call it the cell state, but importantly, this is an element of the hidden state. It forms a cell state at time t as a function of the previous cell state at time t times ft. But ft here is some sigmoid of something. So in other words, ft, importantly, is going to be a vector all containing 0, 1s. I guess that should be 0, 1 to the d here. 0, 1 to the d. Right, so ft is going to be a vector in 0, 1, with 0, 1 elements to the d. And what that means it's going to do is going to take the previous cell state and it's going to scale it down. Right? It's going to scale it down or keep it the same. So it sort of can do anything. It can either, if ft is all zeros, it will ignore entirely the past cell state, or if ft is all ones, it'll remember entirely the past cell state. Okay? This is why that's maybe why it's called the forget gate. It determines how much you forget the past cell state. Okay. But what we're doing is we're forming the next cell state as sort of some scaling of the previous state. And importantly, we have the ability, sort of with the proper weights, if ft is chosen such that it's close to 1, we're largely going to just sort of keep around the past cell state. Then we're going to add to it this term here, right? And this term here, again, is some, it's a term it that is also going to be in 0, 1. And then gt, which is sort of going to be between -1 and 1. So we're adding to this cell state, we're scaling it down, and then adding an additional bounded term, right? This term here, this whole term, I'll sort of emphasize that this whole term here, because you're multiplying 0, 1 times -1, 1, this whole term here would be a -1 and +1 to the d, right? And so what you're doing in some instances, you're sort of decreasing the scale of the previous term and adding a new term to it. And the relative weight of these two terms is decided by, in some sense, this ft and it. Okay? And the sort of important point that I would think here is that, because the sigmoid is saturating, there's a limit to how much of the previous state you can sort of keep around, and you could either keep all of it around or zero it out. Then how the hidden state evolves, to be honest, is a bit arbitrary. This output here, this is just sort of, we're taking some 10H term, so this whole thing will, be a bounded value too. But that's actually the important update, in my view, is this cell state update. It sort of this is where you keep around kind of the memory of the past state, right? So that's the update. And again, I don't want to dwell too much on it because it's just some updates. It has some nice properties. Like you also, by the way, another very nice property here is you have element-wise multiplication of different hidden states here, which is actually quite a hard operation to simulate by other operations. We'll see this again, actually, when we come to self-attention later, or attention in general, 2 lectures from now. So there is an aspect to which this particular form of update also captures nonlinearities like multiplication, which element-wise multiplication, which also seem good sort of separately. But this is the update, okay? And the bottom line of this update is because of this form of the cell state update, you have less ability, or you have more ability to preserve the influence of previous inputs on future inputs. Especially, namely, if I pick, I mean, just intuitively here, if I pick ft to always be 1, if I set it, if I choose it to be all ones, by picking my weights properly, then basically I never would really forget any previous cell state because I am always sort of just adding to my previous state. Of course, you don't always want to remember everything about the past, so you also want the ability to sort of decrease that dependency, but that's the rough intuition, I think. And I think, personally, for me, going much deeper into that intuition has always been kind of a losing battle, and I've never really seen too much value for it. So okay, this is as far as we're gonna go on why LSTMs work. But I do want to mention kind of a little bit of the history of LSTMs here because it's such a really great history. So LSTMs were proposed by Stefan Kredier and Eugen Schmidt-Huber in 1997 was the paper. And I believe actually this paper is one of the most cited papers of the last decade in deep learning. So it's been cited 75,000 times and published. I mean, it's actually the longer you go back, the harder it is to get more publications, because now with these days in modern deep learning, you can get tons of citations by having a really good ConvNet early on in the history of machine learning. But for a paper from the 90s, this is actually quite hard, and so this is actually one of the most cited papers, I believe, in all of machine learning from prior to the turn of the century. The paper was called Long Short-Term Memory, and it introduced this LSTM. But I actually also want to mention, and to be clear, this was a seminal paper. It proposes architecture, and this architecture is not widely used. However, I want to point to another sort of important point in the development, I think, in the development of RNNs, which came from a blog post actually by Andre Karpathy. So Andre in 2015 wrote a blog post called it's called The Unreasonable Effectiveness of Recurrent Neural Networks, or something like this. I'll play on, I think every paper for a while was titled The Unreasonable Effectiveness of Something. It's like something is all you need now in deep learning. It's like a trope. And this blog post, I think, it sort of shows that not every contribution to even academic work has to be in the form of a paper. So this blog post was sort of, in some sense, kind of a fun exploration of recurrent networks, but I think had a huge impact on the field. So this, if you haven't seen it before, certainly go out and check out this blog post. It actually specifically deals with recurrent networks for autoregressive prediction, and it does some very cool things, and it uses an LSTM. And just to make a little point there, I think there's probably I know all of deep learning was exploding at that time, but I think there was a non-zero correlation between the release of this blog post and the explosion of interest in LSTMs, as seen by this inflection point in 2015 when people started using LSTMs a whole lot more than they had before, which just so happened to be the exact year that Andre wrote his blog post. So I think there is some non-zero correlation here, and again, I'm mentioning this because both, I think it's an important example, but it also shows that it's things like blog posts can actually have an impact on the field. Also at that point, I want to highlight some of the things that were produced in that blog post at the time. So as I said before, Andre wrote these recurrent networks that would predict text character by character. And one of the things he trained it on was the Linux kernel source code. And so he trained it on the entire sort of Linux kernel to predict character at a time. And then he used it to generate new text. And this might not be that impressive these days, right? These days we have libraries like Codex and things like this that actually predict real code, so they actually can write real code. But at the time, this sort of absolutely blew my mind. So, predicting text one character at a time produces code that, to be clear, doesn't actually run. So, to be clear, I mean, just to emphasize what this code is. So this code here is sort of saying, okay, now that we have this predictive model, we're gonna sample from it. So we're gonna sort of sample one character from this model. Then we're going to input that character into as the input for an RNN, predict the next character, treat that as the input, etc., and use that as a prediction process. And this process, it produced code that looked absurdly Good. So it doesn't run, of course, here. Like it's meaningless, this code here, but it looks like it could be code from the Linux kernel. It has like comments that terminate and formatting and comments and stuff like this. It's really hilarious. And actually, even more so, one thing I found even more impressive is that I didn't quite see sort of what was really done here, but another example, he trained a similar version on I think it was an algebraic topology textbook, and in LaTeX, and from this generated LaTeX code that actually, with a few, I'm not quite sure how much he's mentioned, with a few edits, actually compiled to LaTeX code. And if you can zoom in on the slide at some point, or download the slides and zoom in on it, it's really hilarious. It writes this text that is, of course, completely meaningless. Again, it's writing text character at a time, but it's writing sentences, and it starts proofs, and then it says things like the proof is trivial and stuff like this. It's really, really hilarious. So I think this post, it really sort of sparked the imagination of what was possible with these models, and I think was not a uninfluential thing in the later development of language models and these sorts of things. Okay, so actually that's the majority of what I want to talk about today for RNNs, but I want to end with two last points talking about more complex things you can do with RNNs beyond just simple sequential modeling. So RNNs, as I formulated them before, several slides ago, they had a sequence of inputs that you're sort of a sequence of inputs x1 through xt, and for each of these you predicted a sequence of outputs. And you had this constraint that the output at time t only depended on things before that time in the sequence. However, both those elements are sometimes things you want to change, right? So that those constraints are not always, in some sense, the right constraints for a prediction task. For example, let's look at a more reasonable sequence prediction task, or not, I shouldn't say more reasonable, a slightly different sequence prediction task, like translating language. All right, so let's take our input sentence here, say something like translating language is difficult. In this case, we're going to produce something like the Spanish sentence, traducir un idioma es difícil. So this translating language in general, actually I picked a pretty simple example here. But translating language in general is very hard because languages don't have a one-to-one correspondence. Right? You can't just translate each word and get a meaningful sentence. There's switches in the ordering of words. There's sort of colloquialisms and sort of phrases that we use in one language that don't really translate to another language. And so you need to not only consider language predictions made word by word, but kind of translating an entire sentence or an entire paragraph sometimes. And it's not immediately obvious how RNNs apply to that, right? So RNNs would sort of predict, take our input translating and predict like one thing from that, right? The point I want to make here, and I won't go into this too deeply, is that there's ways to leverage RNNs to get much more power than this. And one very famous example of this comes from what are called sequence-to-sequence models. And the idea here is that instead of having one RNN that just predicts, a mapping from these inputs to outputs, we actually we use one RNN to parse the whole sequence in some sense. But we don't actually stop there. So we treat this as sort of the input sequence here, but we don't actually stop there. What we actually do is we take the last state of this RNN, which in some sense is like the summary. Remember, a hidden state for an RNN is like a summary of all past text. We actually don't try to have outputs on each of these intermediate states here. We just have this last hidden state. And we feed this into another RNN up top, which tries to generate an entire sequence for the translation. And the way this typically works is that this later RNN on top here would be an autoregressive one. So I'm not actually writing this because it gets a bit complicated. But what would actually be happening here is that this RNN here would make the prediction of the first word. Then it would feed this first word, much like the autoregressive RNNs we saw before, into the next state, predict the next word, feed this into the next word, etc. So you have this chain to predict that, and then of course you don't know when you're done. So at the very end, at some point, it'll predict the RNN would predict the phrase stop. That's how you know that you're done. And you actually also input the phrase stop so the RNN knows it should sort of summarize the text and start turning the output. I don't want to get too much into sequence modeling because this is actually a fairly complex and a whole nother paper in some sense. The point that I want to emphasize here is that what these models did is they leveraged RNNs as, in some sense, a module, right? So this class, we talk frequently about modules and about how we use modules intelligently. What these, and put modules together, once we've coded a module, an RNN module, right, we can put this together to create more, to build up more complex structures. And this is exactly what sequence models are doing. They're taking an RNN, typically used to predict things one at a time, not doing that, treating the whole RNN as sort of as basically an encoder, which maps the entire state it's seen so far, or summarizes it in this one hidden vector H5, and then uses this vector as input to the next to a decoder, which produces the output. Okay, and I don't want to make too much of this again because it is a complex thing, and we haven't talked too much about encoder-decoder architectures here, and that's okay. The high-level point is all of these things, despite their seeming complexity, can effectively be trained in the same end-to-end manner because these are all modules that we have built that can be chained together in automatic differentiation using a tool like Needle, or of course in reality like PyTorch or TensorFlow or these sorts of things. Okay, so that's sequence modeling. And the other kind of important aspect of RNNs that I want to mention, or the other important extension to RNNs that I want to mention, are bidirectional RNNs. So a bidirectional RNN, one feature of RNNs, right, as we had before, so not this version here, but one feature that we had, oops, I copied my figure, so this again should be a Y3 there. One feature we had of RNNs are that the output at time t, x3, depended only on x1 through x1 through x3. So, and similarly, like y2 here would depend in a normal RNN only on x1 through x2. And that's good when we have when our sequence prediction task is such that we don't want to incorporate any future information into our prediction. That of course makes total sense in those tasks like autoregressive prediction, right? Where the target is the next word. So of course, if you use the future of the sequence to predict that, you could do it trivially and you wouldn't learn anything. But importantly, there are many kind of sequence tasks where we want to use the whole sequence in order to predict our output. And a good example actually is language translation, right? There's no reason why we have to use only the sentence up until this current point to predict the next point. We could use the whole sequence. Same with, for example, part of speech tagging in language, right? We don't need to sort of only use the time up to that point to predict the part of speech. We can use the whole sentence. And I actually think that the methods we're going to talk about 2 lectures from now of transformers offer a slightly more elegant solution to this problem. Or even convolutional networks maybe even offer a more elegant solution to this problem. But I do want to mention that there are ways to modify RNNs to allow for temporal dependence to flow both ways. So to remove this constraint that the prediction at time t can only depend on the sequence up to that point. And the most common thing to do is use what's called a bidirectional RNN, which essentially stacks 2 RNNs, one after the other. And of course, you can stack many of these then, but it immediately stacks 2 one after the other, where one of the RNNs runs forward in time here. So this one runs kind of like a normal RNN. And then you stack on top of this an RNN that runs backwards in time. Okay? And the idea here is that with this particular compute graph, you have now joint dependency between all the outputs and all the inputs, right? Because, y1 here has a path of influence from all the other states through the backward RNNs to make its prediction, right? And of course, there's many different chains of influence. In fact, you have this chain of influence, you have this chain of influence, etc. Right? So you have lots of different sort of flows for information through this network. This allows for for essentially dependence in your prediction sequence that it's not just causal. It's not just gonna where the output here doesn't have to just depend on x1 and x2, but also depend on x3. Again, this is not always desired, and in fact, for something like an autoregressive model, this is explicitly forbidden because this would make the problem trivial, and it would make the problem, you wouldn't learn anything from the problem then. But for problems where you want to use the whole sequence, like translation, there's no reason not to do this. And so this is one mechanism for capturing this kind of dependence here. And again, I would be very scared about deriving. I think I could do it for a normal RNN. I could derive by hand the equations for all the gradients. I admit I would not ever want to do that for a bidirectional RNN. I mean, because there's so many different dependencies and chains of dependency here that you have for how different parameters influence other ones. You really would have to basically do it by deriving kind of automatic differentiation anyway to do it in the most simple way. And so I'm very glad that we can just use our automatic differentiation toolkit to just write the forward pass of this thing and immediately get a way of computing all the gradients involved. All right, so that's it for today's lecture. Next lecture, we're going to talk about how to actually implement RNNs. In particular, we're going to implement the LSTM and LSTM's layer. And as we will see, despite the seeming complexity of LSTMs and the frequent, I guess, very long code people use for LSTMs, we'll see it's actually a very simple process in at least at its core level, and we'll use that to build a very sort of short, compact implementation for LSTMs. See people next time.